Right, hydrographs. So hopefully you've had a little read through of slide 5 and you've had a little watch of the video, which shows you in real time what a hydrograph does when you see a stream actually start to flood. So it's a nice little video. Make sure you have a watch. It's not the most interesting video you'll ever watch in your life. I'm fully aware of that, but it is quite useful. So what a hydrograph does, and we're talking in particular about flood hydrographs, because if you're doing extra research on this, you might come across general hydrographs which show you what happens to the river over the course of a year. But we just have to, for the spec, look at a flood one. So what happens during a rainfall event that then leads the river to flood. So we only look at those ones. And what it does is it shows us how a river's discharge changes when we have some sort of rainfall event. And so what that means is if you've got a river, at some point along the river, you'll have like a gauging station where they take river measurements. And in fact, large rivers will have many of these sort of recording stations. And what they'll do at a certain point in the river, do a bit of a cross section, and they'll sort of measure the speed of the water, and they'll have a look how much volume of water is going through that particular section at the same time. And that's what we're interested in. So if you were to do a cross section and you were to work out, there we go, there's the cross profile of our river, and to work out the area of that, so you can then work out a volume of water. If you then look at the speed of the water, you can determine the river's discharge. So it's the volume of water and the speed that we're looking at, because those two things will determine whether, I don't know, city X downstream might flood or not. If we've got more water than usual, then perhaps we'll get a flood. If it's travelling faster than usual, perhaps we'll get a flood. So they're the key things we want to know. So river discharge is the thing that we're interested in, and a hydrograph will measure and show in graphical form what the discharge is doing. So we have certain variables on a hydrograph that you need to know. You need to be able to name them and use the correct key terms for them. Hence, the video will hopefully help with that. So again, as with any graph, we'll have our y-axis and our x-axis. Sadly though, there are two things on our y-axis that we actually end up measuring. So the first thing, and just to make this easy, we'll do one thing at a time. The first thing we'll have is the rainfall, and the rainfall is always shown as a small bar graph in the left-hand corner of our graph. And what you'll have down the side is often they'll do like an extra little sort of axis down here, and that will show you the rainfall in millimeters. And then they'll have like a main axis that will then show you the actual runoff, that then shows you the discharge as well. So the first thing you'll have is the rainfall in millimeters when the storm actually happens, and it'll be a tiny little bar graph in the left hand corner. And so then you have your y-axis will be runoff, and that's measured in cumex, which is cubic meters per second. So as I said, we're looking at the volume of water, cubic meters, and the speed, seconds, and we determine that as runoff. And then so what will happen is you'll then have a line graph that will go along this cumex axis, and that might look something a little bit like this. So where the rainfall is happening, you don't often find that rainfall hits the river straight away. So you will find often that your line graph for your discharge, so wait a minute darling, will be quite low down here. And then as the rainfall sort of finishes, all of a sudden you'll get some sort of peak in your discharge, because it takes a little while for the river, from the water from the rainfall to then reach the river. And you'll suddenly get this very large peak. And then at some point, because the rainfall has gone down, then your discharge level will also come down like that. But it's a bit more complicated, I'm sorry. So this bit that goes up here is called our rising limb of our graph. Then we get to peak discharge at the top. Again, it's more complicated, but they're all quite logical, luckily. And then finally down here, I'll turn it around for a second, this is called the recession limb. Again, once you've used these a few times, you'll kind of get used to it. Or sometimes they call it the falling limb, but the correct one is the recession limb. You'll also see some other things on there. So you might see like a dotted line, a bit like that. And they'll call this bit down here like base flow or groundwater flow. So what they're doing there is they're kind of dividing the water that will flow through the ground and the water that will actually flow over the ground in the river. Because, let me spin it over here. If that's your ground and this is your vegetation or something, when rainfall hits your ground, some of the water droplets will be taken up by the soil and they'll sort of infiltrate and percolate through the soil layers and sometimes the rock layers too. And some of that water won't be absorbed and it will run directly across the land. So what they're saying is that some of the water will actually go through the ground, but most of it will go over the ground, and that's why they kind of divide it in two. Pathway 3 and 4, I wouldn't worry too much about that bit. I'd only worry about the top bit, but pathway 1 and 2, you need to know there's two distinct sections. So the thing we often use a hydrograph for, it's the other thing that you'll then see labelled onto your hydrograph, is we use it to calculate what's called a lag time, and that's really, really important to people who live near rivers. So what the lag time is it's the time taken from the peak rainfall to the time when we get to our peak river discharge. So if I were to draw like a little line up there, it would be that bit to that bit. Remember, across the bottom, you're going to have some sort of time scale. It could be days, it could be weeks. It's normally days. So you can then work out how long it takes that water to get into your river at its peak. That's really important, because imagine you lived near a river and there was a storm. You'd want to roughly know when the water's going to be at its highest, because you'd want to roughly know when you need to protect your house if you live right next to the river, for example. So actually calculating this and keeping records allows people to know if there's a certain volume of rainfall, they'll know that, I don't know, 12 hours later, we're going to have X amount of discharge in our river. It allows you to predict, and it means that you can perhaps lessen the effects of a flood event when it does actually happen. So it is quite useful. Not all hydrographs will look exactly like this one. And what you're going to do in a second is you're going to plot your own hydrographs, and you're going to plot two of them. And there's data for graph A and there's data for graph B. Remember, when you look at that, you're plotting two separate sets of data. Your rainfall, you need to plot as a little bar graph in the middle, kind of make it at least half the size of your runoff so that it ends up in the corner. And then you're going to plot your line graph on your runoff. So make sure you're plotting two separate things, or it won't make any sense. And you're going to plot two of them. Graph A and graph B are very, very different. So what you might find is that one might end up looking like this, a bit like a classic one that I've put in. And one of them might end up looking a bit more like that, for example. And there's reasons why we get different hydrographs, which is what you're then going to do after you've drawn them, and have a look at slide 9. So I'll give you an example. If you've got a very large drainage basin, you're likely to get a very large peak, because a large drainage basin means lots of water, means a big river. You're going to get a big peak. If you've got quite a small drainage basin, you're more likely to get a smaller peak. And vegetation types can affect these, and you're going to look at the steepness of the valley and the soil type as well. And you can probably guess, for example, if you've got a really steep valley side, the water's going to run off really, really quickly, isn't it, down a steep side? So it's going to quickly get into a river. So take a guess, what's going to happen? You're going to get a really sharp rising limb because you've got really steep sides. So hopefully they kind of make some logical sense. But you've now got a couple of things to do. So draw graph A, draw graph B. Doesn't matter if it's on graph paper or not. Just a rough one on lined paper or plain paper is absolutely fine. If you want to be high tech and you want to use Google Sheets or Excel to input it, I don't know if you can with a hydrograph because you've got two separate things. But if anyone wants to give it a go and knows, please be my guest. And then you need to go to slide 9 and work out for graph A and graph B which ones have certain features. So which one has the larger or the smaller drainage basin. Any problems, give me a shout, of course, but hopefully between this and the slides there'll be enough information there. All right, bye.